This is a model rocket, but how do you know anything it's doing in flight, and what if you need to actively control it? That's why I spent the past year making this. This is All Rocket Control, a flight computer I designed for my rockets. It's designed for heavy data logging, active control, and other rocket-related stuff. ARC has 36 screw terminal outputs, along with 6 servo outputs and a ribbon cable connector. The main goal of this project was to improve upon my previous flight computers, which are quite laughable compared to ARC. My previous computer, Ultimate, only had 2 sensors, but ARC has 8. First off, we're going to take a look at the chips. ARC has 23 chips, most of which can be found on Arduino breakouts that you can buy from Adafruit and SparkFun. I did this because these chips already have an existing database, which I can get coding libraries for. These breakouts also have public schematics available, so I know how to use the chip. In addition, if I have some sort of problem with the chip, there's probably someone on a forum who knows more about PCB design and coding than I do that might know what my problem is. The microprocessor on ARC is based off the TNT 3.6. However, it uses a different chip package to make it easier to solder, but it does come at a space cost. The chip runs at 180 MHz, but I overclock it to run at 256 MHz for faster processing speeds. Even though that chip has 62 pins, that's still not enough, so there's a GPIO expander right below the main processor. ARC has 3 IMUs. The main IMU is the B&O 085. This sensor is extremely accurate and also has sensor fusion, but is only accurate to plus or minus 16 Gs. So there's another IMU. The IMU is the LSM6DOS32, which is accurate to plus or minus 32 Gs. There's also a BMI 270 IMU as a backup, and a LS3MDLTR magnetometer. There's also 2 barometers. The main one is the BMP 3090, which is very easy to use and automatically outputs altitude in meters. However, it is only accurate up to about 33,000 feet. So there's another barometer. It is the MS8607, which is accurate up to about 52,000 feet. In addition, the computer needs to know where it is, so that's what the SAM M10Q chip is for. It's a high accuracy GNSS chip that can usually get a connection in about 30 seconds. It would also act as the altimeter if there's any flight going higher than the 52,000 foot rating of the MS8607. Moving on to the back of the board, there's an RFM69HCW radio running at 915 MHz to send telemetry such as its location to a ground station, a DRV8871 motor driver for a roll control wheel, an INA 260 current monitor, an LM2596S-3.3 volt power regulator, a piezo buzzer, and 5 PMP-B10XNX MOSFETs, 2 for cameras and 3 for pyro channels. ARC has 36 screw terminal outputs, along with a ribbon cable connector for the case where you might need a longer range radio. Along with that, there's 6 servo outputs and an SMA connector for the 915 MHz radio antenna. Starting on the right, there's 4 PMW pins from the main processor, then 1 output for the DRV8871, followed by 3 more PMW pins. After that, there's cams 1 through 2 and the other DRV8871 output, followed by pyro channel 3, pyro disconnect, which electrically disconnects the pyro channels, and then pyro channels 1 and 2. On the other side, starting on the left, there's 4 SPI pins, 1 I2C line, and 1 UART output. After that, there's power outputs ground, VIN, 5 volts, and 3.3 volts, followed by a switch output for an external switch, and a ground and VIN, the main power input. I designed the PCB itself in KiCad, and it's a 4-layer FR4 based PCB. It took 5 versions to get everything to work. The 2 versions I use are V4 and V4.1. V4 and V4.1 are almost identical except for the placement of the radio and GNSS. V4's GNSS for some reason didn't work. That chip was the Max M10S. I made several attempts to fix this, but I have no clue why it doesn't work. So V4.1's GNSS chip was changed to the chip I mentioned earlier. Now there will probably be a V4.2 board, because the one problem with V4.1 is that the clock speed of the main microprocessor is only 180 MHz, making it hard to run complicated controls filters like Cowman filters and PID loops. So my plan later this year is to upgrade the microprocessor to the same chip as the Teensy 4.0, which is an extremely fast clock speed of 600 MHz and overclockable up to 1 GHz, which is insane, probably way more than I realistically need. As for data logging, ARC logs to 2 files. One is a massive CSV file with every piece of data from every chip and every data point the flight computer makes. There's also an overlay file, which is how I made this video. This overlay can be useful for seeing where different events happened in flight. That's pretty much it for this video. If you have any questions about this computer, feel free to ask me in the comments section.